All right. So, hello everyone. This is our 8th lecture on quantum computing. And today we will continue the getting familiar with the quantum circuits and the main quantum gates. But so before we start, let me tell you that today we will actually we will start using this IBM Qiskit simulation software. And in your today's homework assignment, you will get some problems to solve using this Qiskit platform. So please register to this system like as soon as possible if you aren't done yet. So to do so, you basically Google IBM quantum experience, and that leads you to this website, quantum-computing.ibm.com. Right, so here on this right hand side, you can find this IBM Meet. You basically click this button and it leads to the registration form. So I already registered it there. I have multiple accounts. So this account specifically for this quantum course. So yeah, as you get here, you will see probably basically two main platforms: this IBM Quantum Composer and IBM Quantum Lab. So we will use this the first one, IBM Quantum Composer, because it provides a nice platform to simulate quantum circuits. So this is basically very like friendly, very intuitive platform to simulate quantum circuits, as you can see. So today we will practice with this platform. We will solve a number of examples, and analytically and using this IBM. All right, so before that, let's go to my tablet screen. And recap what we've done last time. Right, so since the last lecture was on the weekend, right? So not all of you attended the lecture. So let me briefly repeat the main points. Before that, let me turn off the camera to improve the connection. All right. So yeah, just like a summary of what we discussed last week. So first of all, we say that introducing so-called block sphere and block coordinates, which are theta and phi, we can represent any psi vector, which is lambda 0 plus beta 1, right? Alpha and beta complex numbers, and 0 and 1 are orthogonal states of the qubit. So we say that we can represent this using the block coordinates theta and phi in this form. So we represent alpha as a cosine theta over 2, then 0 state, and then plus e to the power of I phi sine theta over 2 state 1. So this is exactly the same state, but written like in another representation. The first one is the alpha beta, let's say, representation. The second one is the block sphere. So important, oh well, because introducing these theta and phi coordinates allows us to represent any state of any state of a qubit as a dot on a block sphere. So this is the sphere with radius 1. This is the axis z, this is axis y, and this is axis x, apparently. So we say that for example, the state number, the state 0 is represented by this point, this sphere. So this is the state 0. This is the state 1. Right. So in contrast to the Hilbert space, in which the state 0 and state 1 are orthogonal, here in this block sphere representation, they are collinear, right? So the angles, this angle theta is basically twice larger comparing to the angles in the Hilbert space, or smaller, anyway. So then this state plus, which is this one, right? So I just remind you that the state plus is nothing but the superposition of the state 0 and 1. And also minus. The state minus is basically the same, but minus here. So basically you change the phase, right? The phase of the qubit. So this is the state plus on the block sphere, and collinear to it on the opposite side of the sphere is the state minus. And finally, the other two states, plus I, this point, and minus I, this point. Again, I remind you that plus I state is nothing but 1 square root over 2, 0, and then plus I, which is imaginary unit, right? And the state minus I, the same but the sign. Up to the sign in the parentheses. Yeah, so as you can see, the block sphere allows us to represent any state of a qubit as a point on this block sphere, which is the sphere of radius 1. And in particular, these most important states 0, 1, plus minus, and plus I minus I correspond to these poles, right, of the sphere. Yeah, and Yeah, just remind you that the theta is this angle from axis z. So it reminds the theta coordinate in the spherical coordinate system, and the angle phi is the angle from the positive direction of axis x in the xy plane. So basically, this theta and phi, they like exactly the spherical coordinates that we use to in math analysis or so. Okay, so this is about the block sphere. Then we started discussing the quantum gates. The last lecture was recorded and available like on my YouTube channel and in the recorded lectures on the FIU Zoom website. So if you don't have access to it, please let me know. And I highly recommend you to watch that lecture again if you didn't saw yet. So we started our discussion with the simplest type of gates, single qubit gates. Single qubit gates. The first gate we discussed was the X gate. I mean, we can like denote it by sigma x. Also, sometimes it's denoted by px, and it is represented by in the matrix representation. It's represented by this matrix 0, 1, 1, 0. Or in the out product representation, it is 0, 1 plus 1, 0. 0, 1, 1, 0. So that's pretty clear. What I probably forgot to mention is that like sometimes, for example, in this Qiskit program software, it is also represented by this sign circle with the plus inside. Alternatively, in the quantum circuits, you can meet this graphical representation, just like a square with just like a square. So, and so what this qubit does, it takes the state and flips it. So that's why it's also known qubit flip gate, or it's like analog to classical NOT gate, analog to NOT gate. So it basically, for example, takes state 0 and flips it to the state 1. It takes state 1, flips to the state 0. Right, and then more generally, why it's called X gate? Well, because it rotates the state around axis X in the clockwise direction by the angle of pi. Right, so for example, as we can see from this block sphere, after applying the gate X, my state 0 becomes state 1, 1 becomes 0, and for example, plus I becomes minus I, and minus I becomes plus I, but since state plus and state minus, they are located at the axis x, so they don't change after application this gate. So the plus I goes to minus I goes to plus I, and plus and minus don't change. Right? So so then this second gate was Z gate. I just follow the last lecture notes and see like what we've done last time. Also known as sigma Z gate, also known as P Z gate, and is represented by its matrix, which is 1 0 0 minus 1. Right, so this is already diagonal matrix with eigenvalues 1 minus 1, and in the out product representation, it is 0 0 minus 1 1, states 1 1. And again, what it does, it basically it operates a similar way. It rotates the state by the angle phi, or 180 degree, but in this case around axis z, again in the clockwise direction. So it doesn't change the states 0 and 1. 0 and 1 don't change. State, for example, z times 0, it is 0. Z times 1, it is 1. But states plus minus and plus I minus I, they basically flip. Like, for example, if I apply z to the state plus, I will get state minus. And if I apply z to the state plus I will get state minus I. In the quantum circuits, the graphical representation is just this box with z inside. And yeah, so next one, this the next qubit is qubit y, also known as sigma y or py, and it's represented by this matrix 0 I, 0 minus I 0, right? Or in the out product representation, it is minus I 0 1 plus I 1 0. This like this gate operates similar way, but by the like change of the axis around which it takes the it rotates the state. So in this case, it rotates around axis y in the positive direction. So it doesn't change the states minus I and I, but flips states 0 and 1 and plus and minus. So the next one, then the qubit number 4 is the most important one. It gets the special name. It's called Hadama gate. Hadama gate. It is represented by the matrix 1 over square root of 2, 1 1 1 minus 1, or in the outer product representation, it is 0, 0 plus 0, 1 plus 1, 0 minus 1, 1. Oops, 1, 1. All right. The graphical representation is the box with H inside. And why it's so important? Because the Hadama gate creates the superposition. For example, if I apply the Hadama gate to 0 state, my the result will be the superposition of 0 plus 1, which is nothing but the state plus, right? So if we return to this block sphere, what the Hadama gate does, it takes the 0 state and makes the superposition of 2, which represents the state plus on the sphere. And the same way, if I apply this Hadama gate to the state 1, it creates the similar state, but up to this minus in the parentheses. So this is state minus. And we will use this fact today. So Hadama gate times 0 state creates plus. Hadama gate applying to the state 1 creates state minus with minus in the parentheses. So Hadama gate creates the superposition, and that's important. And and then we as an example, we have shown that, for example, if you have the gate Z, you can, using the Hadama gate, you can create the gate X in this way. So you basically take the gate Z, apply Hadama gate from both sides, and what you get, you get the gate Z. So using Hadama gate, you can actually change the basis and change the gates. So we've done this analytically last time. So now let's go to IBM Quantum and actually check that this is true, right? So by default we have 2 qubits. So here on the left side you have the number of most important qubits that we usually use to deprogram quantum computer or write quantum circuit. So today we will use just some of them, the most important ones. And by default, this program provides you 2 qubits, the first one, the second one. I mean, they enumerate like qubit 0, qubit 1. Q here means or stands for quantum. And then another line C, which stands for classical, the classical number. So basically the number that you obtain after the measurement of a qubit. So for now, since we now concern about a single qubit state, let's remove 1 qubit from this picture, right? And by default, this qubit is prepared in the state 0. So state 0, usually it is a natural state, like any system ever evolves to the most to the state with the least energy, right? And we just call this state as a state 0. And for example, state 1 is the state with higher energy. Like, for example, you take your atom, and initially your atom in the lowest energy state, you denote the state by 0 state. And when you excite the atom, it jumps to the excited state, which is state 1. Right. So in order to check this, this exercise problem, right? So let's first apply the gate X, which again, this is a circle with little plus inside. So as you can see, the application of this gate X flips state 0 to state 1. So this is like quantum NOT gate. So the result is evolution of the system to the state 1. So now let's check that the same result I can obtain after application of HZH gate. So HZH, I have read this this construction, this operator from right to left, because I first apply the Hadama gate, right, to my state. The Hadama gate creates the superposition, as I could expect, right? So my state now is the combination of state 0 and state 1. And here in the output, you can see how this is represented, this amplitude is represented between the state 0 and state 1. Then I have to apply the gate Z, which basically rotates the state around axis Z, and in this case, this leads only to change of the phase of the state 1 by the phase phi, right? And then I apply the Hadama gate once again, and the result I expect to see is evolution to the state 1. To the state 1, yes. So as you can see, the result indeed coincide with the application of just one X gate. The result is the same as the application of Hadamar, Z Hadamar. Okay, let's go next. And why it's so important, by the way? It's important because sometimes we do the calculations in the in one basis, for example, basis X, but we can measure the qubit state only in the Z state, in the Z basis. So we take our result, transform that result to the Z basis, and then measure it in the Z basis. Or like in this case, we take the result in the basis Z, and then using Hadama gate, we transform the result to the basis X, and then do measurement, for example, on this basis X. Okay, so the next gate was this P gate, P gate or phase gate. Phase gate, which is nothing but just changing of the phase of the qubit. So the matrix is like this one, 1, 0, 0, e to the power of I phi, where phi is this phase. And so the structure of this gate, of this matrix, reminds you the structure of gate Z, but in contrast to gate Z, which has -1 here, this matrix gets e to the power of I phi, which means that this phi, this P gate, rotates the state again around the axis Z, but by arbitrary angle phi. And then two sub gates, let's say 551. It is S gate. S gate rotates by the angle pi over 2. So it is matrix 1, 0, 0, pi over 2. E to the power of I, e to the power of I pi over 2, which is imaginary unit. Right, so it rotates by around Z by angle phi equals to pi over 2. And the second one, 5, 2, is a T gate. Gate, which performs rotation by the angle pi over 4. 1, 0, 0, e to the power of I pi over 4. Right. And finally, the most general type of qubits that we also discussed last time was U gate. And U gate is just like it brings all the gates that we already discussed under the same umbrella, right? So we parameterize this gate by 3 parameters: theta, phi, and lambda. And the matrix is as follows. So it is cosine theta over 2. The second one is e to the power of minus e to the power of a lambda sine theta over 2. Then e to the power of I phi sine theta over 2. And finally, e to the power of I phi plus lambda cosine theta over 2. So yeah, this matrix basically represents all the gates that we discussed so far. For example, the gate with parameters pi over 2 for theta, then 0 for phi, and pi for lambda is nothing but the Hadama gate, etc.
Dr. Alex, I have a question.
Yes.
All the phase gate that you told about, the ST and the phase gate, they're only changing the phase of a state 1, right? Means they're not changing the phase of state 0.
Yes.
Okay.
Yeah. So then we discussed, or well, started discussing the 2-qubit gates. 2-qubit gates. And this part is like very short. So we say that when we put together 2 qubits, right, we and each qubit is represented by its own state vector. then the resulting state vector of the system of two qubits, of interacting qubits, is the tensor product of first and second one. And and this means that the state psi is now represented by the column of 4 elements, not 2, as in the case of qubit, single qubit, but 4, like this. Why tensor product again? Because when we construct the element like this out from the 2 qubits, we basically change our space, right, from the 2-dimensional Hilbert space to 4-dimensional Hilbert space. So it's not a multiplication. This is something something more. Anyway, and as an example, we discussed that, for example, this Bell state, for example, the first Bell state, which is 1 over square root of 2, 0, 0 plus state 1, 1, right? We discussed that like maybe 2 weeks ago, this result, and we noticed that this is so-called the entangled state. This is the most entangled state possible in quantum mechanics, or this is non-separable state. You cannot represent the state as a product of 2 single qubit states, right? So, and we can basically rewrite this result in the vector form or matrix form as follows. So this 0, 0 state is 1, 0, 0, 0. Then plus the state 1, 1 is 0, 0, 0, 1. And the result is 1 over square root of 2 vector column 1, 0, 0, 1. So this is like an example of a vector with 4 elements. So 1 qubit is described by 2 C like 2 quantities, C0, C1. C0, C1. 2 qubits is represented by 4 elements. Right, 3 qubits, as you can guess, it is represented by 2 to the power of 3 elements, which is 8, and etc. So in general, the system of n qubits will be represented by a vector of 2 to the power of n elements. So it grows exponentially with the number of qubits. For example, if you take just 50 qubits and put them together and make them interact, so they will create a entangled state. It will be something like 0, 0, 0, and etc. n times plus state 1, 1, 1, etc. It's 1 n times, right? And this will be like another type of states, and this also will be an entangled state, but this state of n qubits. So this is so-called quantum parallelism. quantum parallelism, which means basically that the space, the Hilbert space, the dimension of the Hilbert space and the number of elements that you use to represent your quantum system grows exponentially with the number of qubits. Is the number of qubits. So, and then we discuss this C0 gate, C0, which is quantum analog of XOR gate. Sometimes it is also denoted by CX, and in particular in this Qiskit, IBM Qiskit, they use what? They use actually the graphical representation. So the graphical representation of C0 is is this one. So it is the shaded circle, like bold dot, connected to this element circle with this plus inside. So this circle with plus inside represents qubit X, right? But now this qubit X is connected to the upper qubit. So this is qubit 1, Q1, this is Q2, and we denote this this point as the control qubit C, and this point is target, control and target. And so why? Because now in this 2-qubit circuit, 2-qubit gate, the state of the target qubit depends on the state of the control qubit. So let's write this truth table of logic of this of this gate. Control, target, and the output, and the result output. So the logic is as follows. So if the control gate is 0, the output is equal to the state of the target qubit. For example, if the state of target qubit is 0, the output is 0. If the state is 1, the output is 1. However, if the state of the control qubit is 1, what this gate does, it flips the state of the target qubit. So, like for example, if the state of the target is 0, then it flips to 1, and if it's 1, it flips to 0. So as you can see, indeed, this is control node, which result basically depends on the state of the control qubit. So how it works in practice? So let's suppose we have this C0 gate, CX, and we apply this to the state 0, 0, for example. So first of all, let's mention how we add qubits to the system. So the state of a single qubit system is represented by this vector, right? For example, state 0, and this is the first qubit. But what, like, how we transform this when we add another qubit. So adding qubits, let's plus q, plus another qubit, second qubit to the system. How we write the state. So in general, we write it this way. So we write this the state of the qubit of the first qubit, then tensor product, and state of the second qubit times state of the first qubit. So again, this is qubit 1, this is qubit 2. So we add the state of the second qubit from the left, from the left. And if we add another qubit, we add this from the left, so it will be written on the left. Yeah, or in short, we write this as a state 0, 0. Just a reminder. So it's very important where is the first and where is the second. So this is the first, this is the second, from right to left, from right to left. So now let's return to to this. So Cx we apply on the state 0, 0. Here we suppose that the first qubit is control and the target is the second qubit. So what is the result here? According to this truth table, the control is 0, so we don't change the target. So the target is 0, the result will be 0, 0. So basically nothing changed, right? Let's go to IBM Qiskit and realize this simple circuit here. So to do so, now we have just one qubit and we need to add another one. So I just click this qubit and click plus. This ends another qubit. So the qubit 0, qubit 1. In my notation, it is qubit 1, qubit 2. Right, and what I do, so initially the state of 2 qubits is in the state 0, 0, as we can see from this state vector diagram, 0, 0. So now I apply this C0 gate, and my result is still 0, 0. Nothing changed. So good, so well. Let's go to another example. So now let's suppose my state is, for example, state 0, 1. 0, 1. So again, my first qubit is control, and the second is target. So in this case, my control qubit is 1, right? So I decided, or I have to change the state of the second qubit, So in this case, my second qubit is in 0 state, so I have to change this to state 1 and leave unchanged the target, the control. So the result must be state 1, 1. Okay, let's go to the IBM. So now we have to change the states of the first qubit, right, to the state 1. I do this by applying this X gate. So now it is state 0, 1. And now if I apply this C0 gate, my result is state 1, 1. Very good. state 1 1. So this is how it works. So now you see, for example, if I apply the C0 gate to state 1 1, for example, I immediately conclude that the result must be equal to 0 1. And like generalizing this concept, I can say, for example, that like I can apply the C0 gate to a more sophisticated state, for example, a state of 4 qubits. Let's say 0 1 0 1 1. Let's say this way, right? And let's suppose I apply the C0 gate with control the second qubit, and the target is qubit number 3. So what will be the result? So my first qubit and the fourth qubit don't change. I don't touch them. So the result will be 0 for fourth qubit. Then I see that my control to the second qubit is 1, so I have to flip the target, so it will be 0. Then control is 1, and the first one is 1. So this is the result. This is how it works. And right now, let's consider this example, which is, by the way, like very important example. This is so-called, I mean, I saw this name, the golden 2-qubit gate, 2-qubit circuit. Golden 2-qubit circuit. Golden 2-qubit circuit. So that's important, and you will see in a minute why. So this circuit gets one Hadama gate, which is H in box, right? And then second qubit. Initially, both qubits are in the 0 state. Hadama gate creates the superposition of the first qubit. And then immediately after this Hadama gate, I apply this C0 gate like this. So let's compute what would be the result. So first of all, when I apply this series of quantum gates, I read this circuit from left to right. So, for example, at this stage, the state of 2 qubits before application of the Hadamar, what would be? It would be the 0 tensor 0, or simply state 0 0. But remember that the first qubit is this one, the second one is this one. That's important. So now we apply the Hadama gate, but to the first qubit. The first qubit in the state 0, and Hadama gate creates the superposition, which is 1 over square root of 2, right? And then the state of the second qubit don't change, so it's still 0. But first qubit becomes a superimposed, right? Superposition of 2. So it will be the state 0 plus 0 state 1. So this is the result at this point. So this is the point 1, this is point 2, this is 1, this is 2. So the number 3, point 3 is application of the state control X, control node, control X gate. So let's do that. we apply the C0 gate to the state 1 over square root of 2, state 0, 0 plus state 0, 1. Oops. State 0, 1. Again, I remind you that the first qubit is this one, second one is this one. First is this one, second is this one. And this is superposition of two. So next, we notice that this control node is connected to the first qubit. So this is the control qubit, yeah. And the target is the second one. So the result will be this, the coefficient 1 over square root of 2. Then the first term here, the first qubit gets 0, so my target don't change, so it will be still 0, 0. And then plus the second term. The second term gets 1 for the control qubit, so I have to flip the target. So it will be 1, 1. So the result of this circuit, of this golden 2-qubit gate circuit, is as follows. So it takes state 0, 0 and creates state 1 over square root of 2, state 0, 0, 0, 0 plus state 1, 1. This is nothing but the Bell state, the first Bell state, which is denoted as this capital sigma with index 1. So what this simple circuit does, it takes two qubits and creates the Bell state. It creates the superposition of two qubits. As you can see, the state is non-separable. You cannot write them as a product of two. Like, for example, this is the stage 3. For example, what was the state at the stage 2? At the stage 2, the state was 1 over, let's write without this prefactor. So the state was 0, 0 plus 0, 1, right? Just combination of these two. But this is nothing but the product of state 0 and state 0 plus state 1. That's it. So this is the second qubit. This is the first qubit. So I can separate the states. I can separate them. But the application of 2-qubit gate makes the resulting state non-separable or quantum entangled, which is nice and gets a lot of applications, and we will discuss them in what follows. But at this point, let me also notice that notice the very important fact here. So in reality, when the circuit does the computations, right, usually the input state is never just like 0, 0. In general, this is the input is the state, the superposition of all possible states. Like in general, the input is something like alpha 0, 0 plus beta 0, 1 plus gamma 1, 0 plus delta 1, 1, right? And the point of this that before I've done the measurement, as you remember, in quantum mechanics, I have to assume that my state is this one, like is before I've done the measurement, I don't know in which state my system is. I have to assume that my system is in all possible states. And this circuit does this computation. I mean, this is already some sort of a like the easiest, not computation, but quantum operation. So this circuit does performs this quantum operation on all the states simultaneously, like in parallel. This is quantum parallelism. So your circuit does the operations on all the states simultaneously. This is quantum parallelism. It's very important to understand this. And another aside here is to mention that I can actually reverse this circuit, right? And of course, you know the result, because in quantum mechanics, all operators, all circuits, etc., they have to be unitary. So if I take the circuit, if I reverse the initial circuit, oops. Meaning that I first apply C0 gate and then Hadama gate, and and my input is the Bell state. What will be the output? It will be state 0, 0. So this circuit not only makes the quantum entangled state, but also does the opposite operation. It takes the quantum entangled state and transforms it to the state of two non-interacting qubits, of separated qubits. Do you have any questions by now?
No, Professor.
Okay, so this is the reversed operation. So it was first aside. This is the second aside, and aside number 3 is that how we like represent in these circuits, how we represent the operation of measurement. So the measurement is represented by another gate in this circuit. It looks like this. So this in this quantum circuits, the state of the qubit is represented by one line like this. So this is the Q, the qubit. The state of like the classical state is represented by two lines, two parallel lines, like this. So this is the state C, like basically the number that we measure in the lab, or measure like as a result of our quantum computer simulation. And the operation of measurement is represented either by this element with a like a measure, right, the scale with the arrow inside, and it goes to this C line either this way, or it's also can be represented by M, which is measurement. Measurement, like, so this is Q, this is classical, and the result goes to the classical baseline. Right, so this is the site number 3. Boom. All right. So this was about the CNOT gate. Let's also discuss the last one. It's called swap gate. Swap gate. So swap gate, I mean, you can guess it's just like exchange gate. So let's, I mean, another name is exchange gate. Oops. Gate. So the graphical representation is like this. There's two crosses connected with connected like a wire, and what this gate does, it does basically it swaps the states of this. It swaps the qubits basically. So if you have a state like AB, then if you apply this swap gate, you will get the state BA as a result. For example, if you have the state 0, 1, then swapping the gates, again, this one is first, this one is second. First, second. The result will be simply state 1, 0. And vice versa. So at this point, we are ready to consider several examples. And I just want to repeat because not all of you were at the beginning of the lecture. So please go to IBM Quantum. Let me show you again. Sign out. Right, so this is the IBM Quantum Experience. You just Google IBM Quantum Experience or quantum-computing.ibm.com. Then you have to register in their system. And this is, I mean, yeah, so you register there, that's like for free. But the environment provides a very nice quantum computation platform. So so you go to the system, verifying. Yeah, so here two main elements are IBM Quantum Composer and IBM Quantum Lab. So the Quantum Lab is just the Python environment where you can write the Python code and play around with them. And for us, the more important is this one, this Quantum Composer. So you go to this one, and as you can see, it provides you the environment with the number of most important gates, along with this measurement operation. So you see this first qubit, second qubit. If you need more qubits, you just click plus and it creates more qubits here. The measurement element connects the qubit, the corresponding qubit, to the line C, which is the classical baseline, right? And yeah, so in your homework, you will be assigned to do some simulations using both ways, analytically and using this quantum Qiskit. So this sphere, this sphere here, they call this not block sphere, but Q sphere. So this is innovation by IBM, this Q sphere. What's the difference? The difference is this phase diagram here. So when you apply single qubit operations, well, we discussed that the block sphere allows you to work with only one qubit, right? Represent the state of one qubit. And as long as you are in the single qubit circuit, like this one, whatever you apply, it's immediately represented over this sphere. And this Q sphere in the single qubit state just corresponds to the block sphere. But what IBM invented here is the ability to represent, to use the same sphere representation, but to represent the state of like 2-qubit system or 3-qubit system, or basically any number of qubits systems. And as you can see, as I add more and more qubits here, I'm getting more and more this like sections over this sphere, and the color of this qubit changes. So this color represents the phase of the corresponding state of a qubit. And yeah, so this is the difference. So this is not block sphere, but Q sphere. So this is about this IBM Qiskit. And now let's consider a simple example. I mean, more sophisticated example. More sophisticated example of this circuit. So let's consider several examples. The first example is, so let's suppose we have 3 qubits, 0, initially in the 0 state. Then first I apply the Hadama gate to the first qubit. Then C0 between first and 0. So it creates the superposition of 2, right? Then I apply Hadama gate to the second one. And right after, another C0 gate between 2 and 3. So the task is to figure out the resulting state. What will be the state of this circuit? So as you can see, this is some sort of a serial connection of 2 golden 2-qubit gates, right? So this is the like the first one that we already calculated, and then this is the second one. So so what is the result of this? Let me go back and go step by step. And the Hadama gate, I just remind you that if it takes the 0 state as the input, it returns 1 over square root of 2, state 0 plus state 1. And if it takes the state 1 as an input, it returns 1 over square root of 2, state 0 minus state 1. So for now, I don't want to keep track of all these coefficients, 1 over square root of 2, etc. Of course, this is just a constant. You can like obtain this constant after normalization operation. So I just want to skip them for a moment and work in the non-normalized basis for simplicity, to make the calculations more tidy, right? So so let's go. So the first operation, again, let's go step by step from left to right as the gates apply. So the first line, the first step here is this one. So the state in this state one is what? It is simply 0, 0, 0. This is initial state. With the first qubit is this one, second this one, third this one. So then the next step is applying the Hadama gate to the first qubit. So the result, the state of the first qubit is 0, which means that the result will be this one, 0 plus 1. So my state will evolve to another state, which is 0, 0, 0 plus 0, 0, 1. Superposition of 2. Then the state number 3 is a result of the application of the CNOT gate with control connected to the first qubit and target connected to the second one. So this is the control here, target is here, control here, target is here. So the state at the third stage of this like algorithm, right? This circuit is this result. So the first control is 0, which means I leave my target unchanged. So this is state 0, 0, 0. And then plus the state 0, 0, 1. The control is 1, so I have to flip the target. So the resulting state will be 0, 1, 1. Very good. So this is the state at the position at the stage 3. So the next one, the state in this the stage 4. So the result, the state at the stage 4 is the result of application of the Hadama to the second gate. The second gate, this one, right? This 0 and 1. So the number 4 will be 0 as the input of the Hadama gate creates the superposition of 0 and 1. So the first one will be 0, 0, 0, then plus 0, 1, 0. And the second one is it gets 1 as the input. I remind you that having 1 as the input gets this state of 0 minus 1. So it will be plus 0, 0, 1. Let me see. Yeah, 0, 0, 1 minus state 0, 1, 1. Right? 0 plus 1, 0 minus 1. Okay. So this is the state. Sorry, the first one is here. The second one is oops, I forgot to let me see. Oh no, this is the state 2. This is the state 3. This is the state 4, right? And then finally state 5, which is the result of application of CNOT gate with control connected to the second and target connected to the third. Again, the control is here, target is here. Control here, target here, control here, target here, control here, target here. Right? Okay. So the state 5, which is actually the result of this problem, will be, this is the control is 0, so it doesn't change, plus control is 1, so I flip the target, 1, 1, 0, plus C0, leave and change, minus flip the target, 1, 1, 1. Okay, so the result of the application of this circuit is the 000 state plus 110 plus 001 minus 111 state. And minus here is important. It represents the phase of the represents the phase of the qubit and of the state, and we have to check that it really changes the color. So let's write this circuit in this Qiskit. So we need the circuit with 3 qubits. So let's create the circuit with 3 qubits. Oh, by the way, I would like to draw your attention to this fact. So when you have 1 qubit, it gets state 0, state 1. And when I add another qubit, it adds the other states, and another state is added from the left. So this is important. Like if I add more, so it gets this another state from the left. So anyway, so 3 qubits. And what I have the Hadama first, then C0 second, between first and second, then Hadama second, then C0 second. Okay, and it's already calculated the result. So what I get, I have state 000, then 001, then state 110, and then state 111 with different color, right? So this blue color corresponds to zeros, either state 0 or 2 pi, which is the same, right? 0 to pi, so the blue color, and the red color corresponds to the phase pi. The phase pi means e to the power of I pi, which is -1, which is -1. So let's compare this result with sorry. I've done. Let's compare this result with the analytical calculation. Okay, looks good up to the swap of these two terms, which doesn't affect the result, of course. So it is state 000 plus 110, 001, and 111 with sign minus here, which takes into account to the phase pi. If I would get the prefactor I, for example, imaginary unit, it corresponds to the phase pi over 2, as you of course know. So so how are you? Do you have any questions?
No, Professor.
No, Professor.
So do you follow all this? Should we consider another example, or it is all clear?
It is clear too.
Yeah, it's clear. I have one question.
Okay.
When I look at the lab, on the IBM,
Okay.
but I see that the control that is there at the bottom is never been used. Control is C4, right, person?
No, this is not no, sorry. Yeah, this is not control.
Oh,
this is classic. So this C here stands for classic.
oh,
You see this double line here. So the classic is always double line.
Oh, okay.
Like shown here. And yeah, so the control like part of the CNOT gate. So this is the CNOT gate, and the control is this bold spot.
Dot, yeah. Okay.
Yeah, and the target is this
the plus sign, yeah.
X, yes. So do you have any other questions about this IBM platform? So there, when you will register, you just need the your email and that's it, and basically like figure out some like choose a good password.
Yeah, I already created an account last week. So
okay. Yeah, very good. So yeah, your homework will be partially in this system, and will be like similar to what we just have done.
So how are we going to submit that? We're going to have to take the screenshots, or we're going to just, there's a way for you to get access to it?
As you used to do. So let me stop the recording first. Stop recording.